We have now entered March 2023, and I'm ready to start on section 2.5. Having studied the proof in the text, not so that I can do it by present it, but so that I understand all the details. And the first problem is to finish the proof when n is even. We have to prove this relation where lambda is defined by this, where n is 16n squared when n is even. So it's just reduce lambda. So that's 2 to 2s n to s divided by 2 to s pi to s and we just write L. All right, so we'll have to prove that this, I'll write it at the bottom so we can copy it to another page later without so much problems. Is there any reduction really, or should we just substitute, 2 minus s? Oops. There we go. So that's what we have to prove. They start taking the Mellin transform of theta sub u of t and reduce it to that should be compared to the definition of L. And where do we have that? That's formula 5.8. I knew I would be using that, of course, so I could have copied it in advance. So. This, of course, being the square. This being the square root of a squared plus b squared, so it agrees with 5a. I just changed it. We need to know to chi n mark when n is even. So I should write it's what is it called? I know in German it's führer. I don't know what the name is in English. I forgot that. And that's 2n. And that should make the computation much more easy than the example when n is odd that they solve in the book, because we can just let a go from 0 to 2n minus 1, and the same for b. So how do we do that? We just write a equals a tilde. That's difficult. A bar plus k 2k times n, and the same with b. There we should use distinct numbers here. So what should we call those? K and L, I think we should use. Oh, K and L was what I used, good. K, N, L, N. And using that it is also modular, yeah, we need both. This is actually somewhat annoying. There's a point there, how they get L and K out of these combinations. I missed that. I'll just substitute it and then write a squared to S. So what do we do here? We need, of course, to take 2k and 2l out. So let's do that. I just need to check that I'm doing the right thing here. In their book, they actually take 4n out, so I think I should take 2n out. So it's squared out here. Do they do that as well? They must. They do it as well, yes. Actually we can take 2n totally outside. Much better. So it's 2n to 2s. Okay, now it's beginning to look like something. So this should be equal to this, and this should for each a and b be equal to this. So we split up the sum. So u equals a bar divided by 2n, point B bar divided by 2n, and M is K point L, and W is 1 point I. So that the scalar product here is this guy, M plus U, K plus, M plus U, times 1, and this guy, L plus this times I. So we have a sum over A bar, B bar, and a sum over M. And a factor 2n, we'll just put that, I'll do it up here. So it's M plus U dot W divided by the norm of M plus U to 2S. That is exactly what we've got here. And now we can exchange that with the proper part here. Let's make that as a fraction. So up we have pi to the s, and then 4 gamma s. That's the sum as well. Right. And they should have a formula for this, which I'll just find. Well, they did it only with their example, so I'll try to redo it using the transformation formula 516. I might be able to write up the result by analogy, but being a little uncertain that I can do it, we'll just make a break and prepare the calculation. I've copied the formula and written up the transformation formula, and that's ready to be applied. We have to sum over u as well. and this is minus I. Just put that up here. 1 divided by t squared theta super u of 1 divided by t. So we make the usual substitution, and then when we've computed the sum, we find out when it can be when we can exchange sum and integration. That's rather an S. So it's S minus 2 oops, it's super. They actually have made exactly this integral, or I don't know if this will become a factor 2, so I have to do it by hand. Now let's do that in its own right. We need the definition of theta super u. And we need the usual integral. So this gives we only have t here, so this just goes out, provided we can exchange sum and etc. So now it's to 2 minus s to here. So it's pi to minus, that's s minus 2, gamma 2 minus s, and then the sum to 2 este. So let's work on this again. So this is the constant that comes out. So let's just look at the constant first. And then from here we get pi to s minus 2. and gamma to 2 minus s. So now we've taken care of the constants. And then we have the sum. And we have to insert, and that was on the other page. So let's forget about the constant first. Or this we set equal to c. So it's c times, now m, I'm so glad I write it, that's k point L, dot 1 point I, 2 pi I, k point L, comma L point, that was A divided by 2n, B bar divided by 2n, and the norm of m that's a little weird. I have a feeling I'm missing something, but let's just carry on. M was k point L. There was a character appearing somewhere, which I've totally forgot about. Yeah, it's here, and here I forgot it. So we'll just put it on. I'll do that in blue. I will do that in blue. Chi n mark of a plus ib. So it should be down here. And here. And here. Here. And then, of course, here and here. And this is the only place where that occurs, the sum over A and B. So let's do that separately. I shall just write it beneath, copy it to the next page, and then I shall carry on. So a little break is in place. That took a little while. I got confused. You see, this is an additive character, of course, but in the last section, or previous section, they compute the g of this character by using the real part of a product of x times something. And that confused me a little, so I had to read the proof again. Now we put 2n out, of course. And then k a bar plus l b bar must be written as the real part. And if it's like in the book, then it should be the real part of k minus il times a plus ib. So let's check that. It's the real part multiplied and the minus the imaginary part, so that agrees. So that means that we can apply the result from problem 9, section 2, I don't know which number. So that means it's chi n bar of chi minus il times, and then it just becomes g of chi n mark. And this is the same as chi n mark of k plus il, the conjugate. I checked this while studying. I don't have a good argument for it right now. Well, never mind. And then G we have from the last 2 sections back. When n is even, it's minus 1. The symbol there times I n mark, which of course, yes, what is n mark? That should be 2n. Yes. I'm sorry about the noise you can hear in the background. It's the neighbor. They are renovating their bathroom and kitchen, so there will be some noise. I didn't want to, since I may be recording intermittently, I didn't want to arrange some breaks where they wouldn't work. But so we'll just have to live with it. Oh, that was the sum. Then we need to insert that in here. So we get the, I'll just make a break and copy all that. I just copied the constant and then waited a little while there was a lot of noise. And then I looked it over and doubted this factor. That seems wrong. And it should of course be 2 minus s instead of s. And then I copied the constant, that's c, and then we have this factor, the symbol minus n times 2in, and then the sum that is exactly L of 2 minus s. So we are approaching what we have to prove. The next step is to reduce it and then see how close we come to what we have to prove. I times minus I cancel. Then we have a factor n, 2 to 1 minus s, pi to 2s minus 2, gamma 2 minus s minus 1 over n. And did I take this factor 2? No. So it's 2 minus s up here. Pi to s, 2s minus 2, gamma. This guy, and n, did we take that? Yes, we did. And divided by 4, that's minus 2 up here. So they cancel. That's 2 to minus s. Divided by gamma s. Oh, I did already write that. Times L of 2 minus s. And we have to compare that with what I needed to prove. And that's what we have here, ready to copy. Oh, it's gone. There, we got it. Yeah. So, we multiply gamma s and 2n to s. I don't get that at all. There's a factor n missing here. All right. So let's just see what I get first, and then it's easier to compare. We multiply this by 2n divided by pi to the s gamma s L of s equals, and then we have gamma s is out, and then it's 2n to minus s, no, 2n to s, and we have multiplied by pi. Now what is this? Yes, that was a pi to s divide by to s, so that we get pi to minus 2 minus s. I think that's what we have there, yes. And gamma 2 minus s, L of 2 minus s. So how close are we? I'll put the green under what is correct. Pi 2 minus s. All of this is correct when this is all right. So it's just the factor n I'm off. So that's pretty good. I'll take a break. Then I'll have lunch. Then I'll look at it. And that should be easy to find. Almost as soon as I turned off the camera, I realized where the missing powers of n would occur. That's, of course, the summation of L. Here we get 2n to 2s. I totally forgot about that, so that's easy. Then I made a little mistake. Where was it? Yeah, this guy should of course be n halves, because it doesn't exist even if n is even, and n is of course assumed square free, so n halves is odd. And then when n is equivalent to 2 modulo 8, then n halves is equivalent to 1 modulo 4, so that gives a plus. And when n halves is equivalent to 3 modulo 4, then this factor gives minus -1, as it should. You can easily find the factor n yourself. There's just the convergence I would like to comment on. When we have a double sum, if the norm of m is larger than, say, 2 times the norm of u, then it can be dominated by some constant for m sufficiently large. So that can be dominated, and that can be dominated by the integral over the two-dimensional integral, where that's it, like from 1 to infinity. And that means that that is r to 1 minus s, and we must have a and this will converge as soon as 2 minus s is negative. So that means we must have s larger than 2. And then in our sum, we then have 2 minus s larger than 2. That was not when I did it last night. So when I record, I seem always to get into trouble about the convergence. I'll just correct it and then start again. Yeah, that is somewhat embarrassing. First of all, up here we have m, and then it's the norm of m plus u to 2 to the s. So that's 2 to the s minus 1. So that means 2 to the s minus 1. So that's 2 minus 2s and then the this constant becomes 3 minus 2s and that means we must have 3 minus 2s being negative, so s is smaller than 3/2. I realized, well, even before lunch, but I'm just recording after lunch, that I needed to prove this relation we used. They use it in the book without comment, but one of the reasons I wanted to record this, my solving these exercises, was first to show, of course, how long time it takes to make mathematics. It's really arduous. The next thing is that I wanted to work out a lot of the details, or rather almost all the details, like domains of convergence. And then, of course, I should prove this one as well, just to remain true to my own goals. First, the definition of chi1 mark. If we have an x, then the different powers one, two, three of I to ix, I squared x, etc. They have these three, four, has distinct values modulo 2 plus I. And of course we assume here that there's no common divisor. So that's the first observation. And since there are only four values, unity, minus unity, I, and minus the imaginary unit, then one of them must be equivalent to I modulo 2I plus I, 2I plus 2I. And that means that we can define chi1 of x so that x times chi1 mark of x is equivalent to unity modulo 2 plus 2I. And that means that x bar is equivalent to 1 modulo 2 plus 2i, and then when we multiply what do? We multiply by x, I don't know really what to do here. Oh, we just take the conjugate of it. And then it's modulo 2 minus 2i, but that's the same modulo. And that means that x bar mark x, my God, x bar equals x1 mark of x. And that's of course equivalent to this guy. And then when we go to xn, it's a real factor plus minus 1, so that means it carries over to all of the xn's. So I believe this proves this proposition, and it was used in the proof.